Welcome to the course Advanced Reaction Engineering. So, in this course we today will discuss about the collection and analysis of rate data. So, already in our previous class we already have discussed about how to find the rate law from the for a particular reaction. So, by considering various reaction steps, adsorption, surface reactions and desorption. So, the rate equations we can evaluate that way by considering a particular method. So, there are many methods that we already have discussed. So, Langmuir-Hinshelwood methods, Elie-Riedel methods, Marsh-von Kraepelin methods, many methods are there to find out or evaluate the rate equations. So, now in general the rate equations we usually express for the simple batch reactors or differential reactors usually minus dCA by dt equals to minus RA. So, that way usually we write the rate, and whenever we conduct any reactions for any batch reactor by considering. So, let us say we have a batch reactor, this is a batch reactor. So, here we can charge a reactant. So, and then let us say Ca initial concentration of A, that was Ca naught. So, once time will pass at a particular temperature. So, let us say 1 hours is required to complete the reactions. So, then at different times, so if we measured the concentrations like that. So, like that. So, if you take out sample from here, this is a batch reactor. So, and 0 times initially it was initial concentration of the reactants, and so once time is passing t equals to 1, concentration is Ca1, t equals to 2, concentration is this, t equals to 3, concentration is this. So, that way for up to 1 hour. So, we can collect samples from here and we measure and analyze the reactant concentration Ca we can get. So, this is from the batch reactor data we can get, and so normally the rate we can express minus dCA by dt. This way we usually write rate equation. So, for homogeneous reactions, so if we use means batch reactors usually homogeneous reactions, for that we usually use, and for gas and solid reactions or liquid solid reaction, that is called heterogeneous reactions. So, for that differential reactors usually use to find the concentration of the product or reactant concentration at the end of the reactions or exit of the reactor. So, that way we can evaluate both the way we can find out the rate of the reactions, means for batch reactor this to get the rate data, and for differential reactor for heterogeneous reactions. Okay. So, from the experimentally if this is the reactions, so this is the temperature against concentrations, this data we usually obtain. So, now and for the differential reactors, so for run set of run 1 to 3, partial pressure of A, B, C, 3 components are there. So, at different times, so different set of data, that way we can evaluate from the experiments. So, similarly another set of data also, that way set 1, set 2, set 3, set 4 by changing a partial pressure of A and partial pressure of B. So, that way we can get a number of data sets. Okay, that is the experimental data. Experimental data or experimental obtained data, this is also experimental data. Okay. So, this is for batch reactor, this is for differential reactor. So, this is for homogeneous reaction and this is for heterogeneous reactions, this data we can use. Now, since the reaction is this, stoichiometry is this. So, now you have to means here the partial pressure with respect to the rate for the differential reactor. So, is given here. So, when these sets of data is there, corresponding rate is this. When these sets of means concentration or partial pressure of individual component is there, then corresponding rate data is this, like this. If we change the concentrations or partial pressure of individual component, corresponding rate also would vary. Okay. So, now the experiment data we have. So, now our objective is or we are going to discuss about analysis of those data, and by considering various methods to evaluate a rate equations or rate parameters, maybe order of reactions or reactions rate constant or specific reactions rate, that we can find out. Okay. So, there are many methods, differential method of analysis is there, integral method of analysis is there. So, and nonlinear regressions techniques or linear regression techniques, many methods are there. So, only these three we will discuss basically. So, other methods are also available. Okay. So, now let us say these reactions, and this is the rate equation, okay, minus R equals to K into C to the power alpha, when reactant A was there, and when two reactants are there A and B, here reactant was 1, rate law is this, when two reactants are there. So, then rate law we can say like this, minus R equals to K A C to the power alpha C B to the power beta. So, alpha and beta, these are the order of the reactions with respect to the A and B. Okay. And here specific reaction rate is K A, here is also specific reaction rate K A, or here it is alpha. So, these reactions if we consider when A plus B going to product. So, then if we consider that B that we are using, that is another reactant in excess amount. So, then concentrations remain unchanged during the reactions, only the amount of A will charged inside of the reactors. So, then reactions will proceed and then would be completed. So, then these rate equations we can write this way, minus R equals to K prime C to the power alpha. What is K prime? K prime equals to K A C B to the power beta, or we can say K A C B naught to the power beta, K prime. So, now these reactions when excess B is A is used, same rate means here excess B was taken. If we take excess A, then the reaction similarly the rate equation in terms of concentration of B we can write this way, okay, either this or this. Okay. So, here K double prime equals to K n C to the power alpha. So, means the rate equation simplified way or simplest way we are expressing. So, now this specific reactions rate and beta we have to find out. So, then actual rate with respect to the concentration changing. So, how that is varying, that we can find out. So, I said differential method of analysis is there, that already you have studied in our UG class, again we will discuss. Okay. So, this is for let us say constant batch reactors is there, means the reactors volumes is constant. Okay. So, volume is constant. So, in this case constant batch reactors we are considering, and we are conducting the reactions here. So, here the rate equations we can write this way, minus dCA equals to by dt equals to K C to the power alpha. If you take log both side, left side and right side, we can write this. Okay. So, now if we know that this is the rate minus dCA by dt. So, minus R A equals to minus dCA by dt. So, this is the rate. So, if we know the rate data, time, concentrations minus R A. So, this data should be there. So, from experiment this we can find out, then rate we can evaluate, and then once we know the rate. So, this against ln CA if we do plot. So, if we plot this, so then this type of curves will come. Okay. Data points would be dotted line, dotted, this dotted is the data points. So, here's ln minus dCA by dt ln CA, CA was there, if we take ln and minus R A we can evaluate it, and that we can put it here. So, these data points we can get. Okay. So, now if we plot y axis this in terms of ln and x axis we are plotting ln CA. Okay. So, if we plot this way, then dot, these would be the dotted lines, and then one straight line we can draw. So, then we can get the slope. Okay. So, slope we can get the slope, and intercept also we can get. So, if slope equals to alpha, so then alpha easily we can find out, and from the intercept equals to ln K A. So, then if you know the intercept value, then K value we can find out. So, this is the differential method of analysis, or if you want to, if you know this value and CAP product concentrations, from there you can get this value and this value. So, you can put here alpha value is known, then K reactions rate constant we can find out. Okay. So, now concentration and time experimentally we can find this, and how to find minus dCA by dt. Okay. So, this is important. So, here we have discussed from the experiment this data we can get, but how to get this rate data, how to find out. Okay. So, that we will basically discuss. So, what are the various techniques are there. So, only concentration against temperature data we have. So, usually temperature and concentration. So, usually this way C naught it would vary for component A. So, this data or graph we have. So, from here how minus dCA by dt we can find out. Okay. So, there are so many techniques are there, means this data experimentally we can get for batch reactor data, constant volume batch reactor data at different times we can get corresponding concentrations. Okay. So, now there are methods, graphical method, graphical differentiation method is there, numerical differentiation formula or methods is there, and a polynomial fit to the data is there. So, these are the data or table we have. From here graphically how we can get dCA by dt. Okay. Means at this different this point, this point, this point, this point. So, how minus dCA by dt value we can get. Okay. This value we have to find out. Okay. So, these are the methods, graphical methods, numerical methods and polynomial fit is there. So, one by one these methods we will discuss. Okay. So, first graphical methods. Okay. Number one is the graphical methods. We have these two data points, means temperature against concentration, this data we have. So, now we have to find out this data. Okay. So, first this is temperature means at different times. So, these data points we can write this way xi yi, okay, concentration in terms of yi. So, here equal differentiations, equal area differentiations we have to take. Okay. So, here x1 minus x2 we can get, that is delta x, y1 minus y2 that is delta y we can get from point 1 and point 2, the difference we can find out, and then we can find out delta y1 by delta x2, delta x, delta y by delta x by considering these two data. Okay. So, like that x2 x3 y2 y3 this data point we can get, this data point also we can get. So, first this, next this. So, this delta y by delta x, these data points we can get. Like that other data point also, set of data points we have from the experiment. So, like that delta y by delta x 4 we can find out. So, like that delta y by delta x 5, delta y by delta x 6, like that we can get this. So, we have this and x axis this time is there. So, now we will plot, this is equals to delta y by delta x and against t we can say, or here x against this and this, here minus d delta Ca by delta t against t we are plotting. So, if we first points we need, that way we can equal differentiations area, means this type of data points we can get this like that. Okay. So, this type of data we can plot this. Okay. This is y axis, this is x axis, we can plot that. So, at this particular points this way you can get. So, now at this particular point take here red data points, here data points. So, this area under these triangles and these triangles should be the same, such way the height we have to take this point and this point such a way that the area of A and B should be the same. Okay. Then these two data points we can consider. Like that also another data points here also take. So, like that these dotted points we will get from this graph, and then we have to join them all dotted points, then a smooth line we can get. Okay. So, this is smooth line we can get, and x axis time is there and y axis at any time. So, now if we want to get at this particular points, what would be this value, and corresponding from the lines whatever the data points will get, that would be minus dCA by dt points. Okay. So, this way we can, this is the graphical methods, and this methods means not very accurate. So, we can also apply this method to find out minus dCA by dt from this. So, by this way these data dotted points we can get and corresponding dCA minus dCA by dt value we can get and make the tables. Okay. So, there is a second method, that is the numerical methods is available. So, here 3 different points and corresponding so we have these data points, temperature, a time and concentration value we have, this we do not have. Okay. So, for initial points at t equals to 0 points, this is value. So, at this particular point minus dCA by dt if you want to measure. So, then say here dCA by dt at t equals to 0 point, Ca naughts we know, Ca 1 value, Ca 2 value we know, and delta t value we have to put. Delta t, what is this? T1 minus T0 equals to T2 minus T1, equal spaced value we have to consider, and then to get initial points. So, this way we can get this value. Similarly, the last point initial point, last point also we can get, let us say this C3, C4, C5, C5 is the last point, C5 is the last point, C5 known, C4 is known, C3 is known, delta t is known. So, then all these components known value points we can put there, and if we multiply with 1 by 2 delta t, then fifth points we can get. So, these points we can get, this point gets, intermediate point also or interior points we can get by using this. So, this way we can find out. So, like that. So, all these data points we can find out. So, red means if we know the time against concentration, that data point experimental we have, from there red data minus dCA by dt we can find out. Okay. So, this way we can numerically the second methods we can find out, and third one is the polynomial fit. This is the most easiest method, since nowadays we can use different computer softwares and Origin, Excel, anywhere we can plot this and we can get the data. Okay. So, it would be much more easiest and easiest way. So, now we have this C against temperature data. So, we can plot them, C against temperature data we can plot them this way, these data points we can get, this is the experimental data points. So, once we plot them, after that we have to get a fit that data with the nth order polynomial fits. So, the data will get from this software. So, Ca equals to some value, let us say 0.02 t square plus 0.05 t cube, like this data points will get, means this data would be fitted like this, or it nth order polynomial that would be fitted. So, equation 7 will get, and after that this we have to differentiate with respect to the time. So, if you differentiate this with respect to the time, so we will get this equation 8. After differentiations equation 7 with respect to the time, then dCA by dt we can get this. Okay. So, now this differential equation, first order differential equations we have. So, now if we want to get t equals to 5, let us say, that corresponding minus dCA by dt want to know. So, here if we put t equals to 5, so then corresponding A1, A2, A3 value is known, this A1, A2, A3 value is known, then corresponding dCA by dt value will be evaluated. Similarly, if we put t equals to 10, so at t equals to 10 minutes we can get dCA by dt at 10. Okay. Like that, all data points of this minus dCA by dt, that is the rate for the batch reactors we can get. Okay. So, how to get this means this data from the experiments will be collected, and then by using polynomial fits we can get these data points. Okay. These data points, it is already given, this is also given, this is also given, this is given, all these are given. So, these are the value from that polynomial fits we can get the data points of this value. Okay. So, now we have this concentrations and this minus dCA by dt value. So, now it would be easy for us. So, these data points and these data points we have. So, if we plot them, so in ln minus dCA by dt against Ca, that is also ln, means ln Ca ln this. So, many data points we can get. So, all these data points. So, then we take a straight line. So, then it would be get corresponding slope and intercept we can get. So, these are the points we will get. So, if intercept is this and slope is alpha, by that way alpha and Ka value we can evaluate. Okay. So, now determine the rate law. One example we will take, and there's from the experiments. So, let us say this is one reactants, this is another reactants, both will means if we take any batch reactors, there we can conduct the reactions, and after that these are the product formations would be theirs, and the reactions let us say was conducted at 25 degree centigrade, and initially the concentration of A that was charged this mole, initially the concentration that was charged. Okay. So, this is actually Ca naught basically. So, now at different times, if we after charging A and B, if we wait up to 6 hours, let us say the reaction is very slow. So, 0 minutes initial concentration was let us say this, and after 50 minutes we will get these concentrations, after 100 minutes 150 like this, 200, 300, this is the experimental observation, the concentration of A. So, concentration of A initially it was high, and with progress of the reactions concentration gradually decrease. So, initially it was 50, and then after t equals to let us say 0 to 300 minutes. So, here the concentration would be 17.4. So, it is dropping that way. Okay, this is the experimental data. So, now we have to find out the rate equations, the rate order and reactions rate constant for this particular reactions by using we have already studied 3 different methods. So, using 3 different methods, so what would be the rate or rate constants or reactions specific reactions rate order we can find out. So, graphical method we know, finite difference method and polynomial methods, these are the 3 methods we have, finite difference method or numerical method and polynomial methods we have studied. So, now these are the data points we have from the experiments. So, from graphical method if we first apply, so then minus delta C by delta T, that we can find out for this data point. From these 2 data points and these 2 data points we can get this, using these 2 data points we can get this, like this we can get this way we can fill up this. So, now we have to plot them, this and this against time we have to plot, and from there by graphical methods we can get this value. Okay. Minus dCA by dt we can get from graphical methods. Okay. So, one data point how that has been minus delta C by delta T, that equals 2.4. So, the first data points it was shown here how it has been evaluated. Similarly, this data point, this data point, this data points all can be find out, and then if we plot graphically, so from there equal spaced area this we can find out by drawing a straight line. A straight line means this smooth line, this lines, draw a smooth line, and by that way these parameters we can find out. Okay. So, graphical methods we have discussed. Now, yeah, so here's, so equal spaced area we can find out, and by this way we can get the rate data. Okay. Similarly, finite difference methods or numerical methods also the equations is given at t equals to 0, t equals to 50. So, how the rate we can find out. So, concentrations Ca naught, Ca, Ca2 is given, delta T you know. So, by that way you can t equals to 0, t equals to 50, like that other data points also we can find out. Okay. So, now polynomial fits also similarly, one concentration against temperatures concentration against time that was given. So, we can plot them C against T. So, the data points would be like this. So, if we draw a smooth lines, the lines would give a this nth order, 4th order polynomial fit, it was fitted 4th degree polynomials. Okay. So, these equations we get. So, now differentiating this we will get this. Okay. So, by polynomial fits. So, now at different times we can get the rate. So, here it is summary of the data how we have evaluated. So, at different times here time is given, here from the graphical method, method 1, this is method 2 and method 3. So, minus dCA by dt that was evaluated this, and from these methods minus dCA by dt we has evaluated this, and by using polynomial methods it is this. This is the concentrations at different time respective times. Okay. So, method once you can see the rate is for graphical method 3 at t equals to 0 it is coming 2.86, it is coming 2.98. Similarly, at 300 minutes if you take, so graphical method it is coming 0.42, but finite difference method is coming 0.36 and polynomial fit it is coming 0.33. So, these two value almost closed to each other. So, there is no significant difference in between these two value, but here significant changes or difference you can notice. So, therefore, this method is not much more accurate. So, therefore, either finite difference method or polynomial fits either ones we can use to find out the rate. Okay. So, now rate data we have, concentration data we have, let us say polynomial fit is there. So, experimentally this concentration we can find out at different time, and polynomial fits we can get rate data minus dCA by dt. So, this is the rate equations for the let us say first order rate equations. So, here's 1 by 1's ln CA means here's this value ln minus dCA by dt we can get, and min ln CA. This value means we have this. So, its corresponding ln 2.98, what would be that value? This is also ln 1.88, corresponding value we can get, and ln CA equals to ln 50, ln 38, like that. So, what are the value would become? So, we should put it here. So, these tables we have to complete. Once it is so many data points we will get at different times. So, now we can plot them. So, minus dCA by dt against ln CA, if we do plot, this is also ln. So, then maybe different data points it may come. Okay. So, like that. So, if we get different data points, so this is intercept and this is slope. So, from here we can get, let us say this was our rate equation. So, k prime we know, and that value and alpha value that would be evaluated. K prime equals to we said that is k1 into Cb. If we consider beta equals to 1, so then k prime equals to k into Cb. Okay. So, or we can write this k prime value that is known from the this here, we can substitute here. So, or these rate equations we can write minus r equals to k into Ca to the power alpha into Cb. So, here's alpha and k value means here if we put k prime value, Cb value is known. So, then k value we can evaluate. So, k value we can put it here, let us say here it is we are putting 2.44 k, and Ca alpha equals to 2, let us say here. So, alpha equals to 2 Cb. So, this would be the rate law. So, this way rate law parameters means this was our rate. So, here beta equals to, we are assuming 1, alpha equals to evaluated 2, and specific reaction rate constant 0.244. So, this way you can evaluate easily, we can find the rate equations for this particular reaction. So, now today we have studied various methods, means from experimental data we have concentrations and time for the batch reactor, constant volume batch reactor, from that how we can get the rate data by using various methods that we have discussed. So, now it would be easy for any linear equation, nonlinear equations to means find out reactions, specific reaction rate constant and order of the reactions to evaluate. Okay. So, today is up to this. Thank you.